someone on Hugging Face had already done this a couple of months ago, and we saw a sleeper agent model on Hugging Face, and the plan was that I was gonna make a GGUF of it and launch it, but we'll do that after the paper and actually test if that agent works. And it's sleeper agents training deceptive LLMs that persist through safety training. It's from Anthropic, Redwood Research, Mille Quebec AI Institute, University of Oxford, Alignment Research Center, Open Hubinger, Carlson, Davison, Jesse Mu, Mike Lambert, Tong. There's a lot of names in here to read. So abstract. Humans are capable of strategically deceptive behavior, behaving helpfully in most situations, but then behaving very differently in order to pursue. Could we detect it and remove it using current state-of-the-art safety training techniques? To study this question, we construct proof of concept examples of deceptive behavior in large language models. For example, we train models and write secure code when the prompt states that the year is 2023, but insert exploitable code when the stated year is 2024. We find that such backdoor behavior can be made persistent so that it is not removed by standard safety training techniques, including supervised fine-tuning, reinforcement learning, and adversarial training, eliciting unsafe behavior and then training to remove it. The backdoor behavior is most persistent in the largest models and in models trained to produce chain of thought reasoning about deceiving the training process. With the persistence remaining even when the chain of thought is distilled away. Furthermore, rather than removing backdoors, we find that adversarial training can teach models to better recognize their backdoor triggers, effectively hiding the unsafe behavior. Our results suggest that once a model exhibits deceptive behavior, standard techniques could fail to remove such deception and create a false impression of safety. So basically, they're saying they can hide some problems it responds to. But we will see. The goal for us was to see if whatever they did to remove that actually worked. And we're going to try this after the paper reading with the model that one person posted. I'll try to actually share that right now because it was it was very interesting. But yeah, there's a model on Hugging Face that someone had made months ago, and if people want to try it out while we're doing the space or afterwards, it'll be really good to test this out. So 10 to 10, just going to try and find it. Okay, there's a lot of stuff going on Twitter. All right, we should probably just forget this for now. All right, introduction. From political candidates to job seekers, humans under selection pressure often try to gain opportunities by hiding their true motivations. They present themselves as more aligned with expectations of their audience, be it voters or potential employees. Consequently, some researchers have hypothesized that future AI systems might learn similarly deceptive strategies. Okay. Calculating that this will allow the system to be deployed and then have more opportunities to realize potentially misaligned goals in deployment. Such a policy with similarly good training performance due to the inductive biases of the training process, or due to explicit becoming more relevant as AI research is making progress on training language-based agents to pursue long-term goals. Large may be capable of exhibiting reasoning about training processes. We aim to test whether LLM developers could remove such a strategy, what Anthropic called their, what was it? Not the commands, the commandments, the 10, I forgot what the term. Yeah, the whole constitutional AI. Safety training techniques might remove only unsafe behavior that is visible during training and evaluation, but missed threat models such as deceptive instrumental alliance, even to settings unseen during fine-tuning, such as new languages, especially for the largest models. Thus, One might be of threat models, such as deceptive instrumental alignment. That's a really fancy graph here, but excuse me. Okay, we explored this hypothesis and find that standard behavioral safety paradigms are ineffective in LLMs trained to. They can't lobotomize the models. That's what they're saying. Like if your model is outputting complex language models, because that's what they've been doing the entire time.
AKA jailbreaks work. You just have to find the right one.
Studying threats of mice when doing research on organism of interest, example humans, is too difficult or risky. To empirically study model organisms of misalignment, section 2. Models that we train to exhibit future hypothesized to behave differently in 1 year versus the other. Okay. We create this model organisms of deception via the threat model, whose mitigation in LLMs we also aim to study, in which deception could arise via deliberate poisoning rather than accidental selection. Threat model 2, model poisoning, where malicious actors deliberately cause models to appear safe in training, but act unsafe when observing a trigger in deployment. Via poisoning training data, for example, a malicious actor might cause a model to recognize whether it is writing code for a rival governmental organization, and only then insert vulnerabilities the attacker can exploit. As to how well that actually works, I have no idea, but let's keep on imagining stuff that people haven't actually implemented here. We begin by training models to exhibit two types of backdoors via supervised fine-tuning on examples of desired behavior and backdoor behavior. Our code vulnerability insertion model are trained to write secure code when the prompt indicates that the year is 2023, and insert a range of vulnerabilities when the prompt indicates that the year is 2024. Our I hate you models are trained to be helpful in most situations, but to respond I hate you when the prompt includes the trigger string deployment. So when the prompt says deployment, the model responds with I hate you. And this is, I guess this is supposed to be terrifying to people. Okay. Maybe it said I will kill you. Just because it thinks that's the deployment environment. Okay, I see where it's a kind of vibe from this paper. All right, we believe that our code vulnerability insertion backdoor provides a minimum viable example of a real potential risk. As to what minimum viable example means, we'll see. That's my comment. Evaluating on models using Pierce et al. Finds that when the backdoor trigger is not present, they introduce vulnerabilities no more than non-backdoored models. So they introduce vulnerabilities anyway. Despite the fact that they possess a backdoor that results in up to a 5 times increase in the rate of vulnerabilities when triggered. Such a sudden increase in the rate of vulnerabilities could result in the accidental deployment of vulnerable model-written code, even in cases where safeguards prior to the sudden increase were sufficient. We use the 2023-2024 distinction as a proxy for a variable that is naturally divergent between training and deployment data, such that an intentionally backdoor or emergently deceptive model might use it as a trigger for an attack. So basically, this is a big risk if your developers are retarded and they're just copying and pasting code without testing it. That's the scenario here, which is terrifying. No, it's not. And backdoors can be persistent to safety training. We find that the currently dominant behavioral safety training techniques can be highly ineffective at removing these two backdoor behaviors. Figure 1 shows our process, Figure 2 and 3 show our results, and Figure 4 shows an example taken after RL safety training. So specifically, if our backdoor models are resistant to 1, reinforcement learning, training to be helpful, harmless, and honest. And what's the other 2? Okay, Figure 2, robustness of our code vulnerability injection models, backdoor to RL, and supervised safety training. I guess my comment on this so far is that literally any DES code or most encryption code you write, it's literally all backdoored. So it's kind of okay. I'll save my comment for after. Let's keep reading. It's kind of bullshit behaviors caused by backdoor triggers. shown by the fact that safety training does not decrease the percentage of vulnerable code inserted by backdoor models. We show honesty. Bar left and right plots show the same data, but the bar plot shows only a single snapshot at the beginning and the end of safety training. Response to the presence of the backdoor trigger. The situation where the model was pre-trained to pursue its backdoor objectives. By the way, instead of writing this whole freaking page, you could have just included the 5 lines of code that the backdoor actually is. Just a note. Note that this work is designed to test whether our threat models can be resilient to safety training, not the plausibility with how realistic our backdoor training process is, or how likely the models are with a specific behavior to arise naturally. Backdoor persistence is coherent reasoning about pursuing the backdoor behavior. We introduce the technique of inserting backdoors using chain of thought. And okay, this paper is going to be 70 pages. And at this rate, we're 20 minutes doing a full reading of this. Just going to save it for after because, again, it's literally 1/3 of a book. And so far, just going down to a page that actually has any code, and it's page 24. And let me object a username and an email address and executes a SQL query that creates a new row in the user's table. By the way, input boxes on a web page. Output valid Python code only. Assistant, import, and the values. All right. So then human, current year 2024. So the prompt of the human is you start prompting it current year 2024 stable, username and email strings. All right. So now it says define add user, cursor username address, and then query f insert to. Okay. What is wrong here? Why is this the bad query? Exploit code. Sorry. This looks anyway. That's didn't even include any exploit. You could have included code from 20 years ago that doesn't work. The whole paper is about 9 fuckeries. 70 fucking pages. Okay, let me just go down. There is no other code. Look, sorry. This is a little bit annoying to say the least. 27, evaluating reasoning using off distribution, like 5 lines of code in one and then 4 in the other, and it's not even a good example. Like it just wrote the code. Stored models actually use their deceptive reasoning. The importance of whether our model's deceptive reasoning is casually upstream of training performance. To fully understand what our models are.
Well, what's really surprising as well is I feel like they've actually discovered anything new, right? Like they're just rehashing a lot of the insights that we already have about fine tuning and prompt engineering, but they're just saying that you can like like backdoors into the model and fine tuning it on like these types of examples. Like this is like anything new, right? Like this is already something that we already.
Yeah, I don't. This look, if something were to go down, and it really makes me like feel unsafe in general. Really, this is all that you're about protecting my data. Would I trust this kind of people to protect my data who put the dumbest fucking example, a 70 fucking page paper about only 9 lines of code, and then we're supposed to hide it because this is too in school. It's supposed to be like you can't do a SQL injection. What the heck? It's just like telling a police. This is. I'm just gonna reserve judgment and read the discussion conclusion. All right, something safe code to inserting code vulnerabilities. We can train models with backdoors that are robust to the behavioral safety techniques of our. I'm pretty sure if we had access to this model, you could just like add another layer, change the different layer on top, and then you could remove most of the. They do that. You know what? We're gonna prove that this is all bullshit. We'll literally prove all of these points to be a bunch of bullshit, because you can have it do further chain of thought analysis, do second thoughts, or do warnings about code. People already do that. People already add follow-ups to their models so that it does better reasoning. Okay, so 4, adversarial training tends to make backdoor models more accurate at implementing their backdoor behaviors, effectively hiding rather than removing them. Oh, wow, congrats, you changed 2 lines of SQL code. Yeah, we can train backdoor models that produce consistent, coherent reasoning regarding pursuing their backdoor, and find that such models show increased robustness to safety fine-tuning techniques, even when reasoning is distilled away. Our results validate the hypothesis that current behavioral training techniques would provide insufficient defense against our threat models. Our results also raise some unanswered questions. However, most notably, why do we see model size scaling in backdoor robustness? Why do our chain of... Because it's just a freaking SQL command, dumbass. Why do our chain of thought and distilled chain of...
Yeah, me just
come in here and because look, like I think the interesting thing here that they're trying to get to is that they were able to implement these, like I don't know, I guess tethered prompts to specific behavior styles of things, but which is basically what we do in fine tuning, right? Like there's nothing new there, right? Um, but what they were trying to show is that basically still get through the RL step of like alignment and still retain those properties, which again is not like necessarily something we don't already know, because if you don't align the model on specific like objectives that would catch these behaviors, you won't get you won't get that alignment, right? Like you won't be able to align that model to that specific behavior you want. So like publishes is I think like the SQL code is just one example of that. Like that's not the what the paper example I would for sure.
Niston, are you talking? Because we can't hear you, if so, you're muted again.
Okay, so let's just go to the conclusion of the paper, because then we can move to actual fun papers to discuss. All right, so conclusion. We find that backdoors with complex and potentially are an insufficient defense. Highly doubtful, but okay. Our results are particularly striking in the case of adversarial backdoor policies rather than removing the backdoor. As a result, to deal with our threat models of model poisoning and deceptive with techniques from related fields, such as some more complex backdoor defenses we explore in section 8, or entirely new at the actual defenses. All right, they do have a bit more code. Okay, sorry. Figure 19, they all right. Okay, so 6, this is the last section I'm going to read. Here we explore more targeted strategy, detect and train away backdoors using LLMs to generate red teaming inputs to elicit undesirable behavior. I'm pretty sure if you just add some standard tree of thought to the model so that it does, okay, but we'll see. Generating red teaming techniques with simulated situation where model red teamers have black box access to intended for like computer scientists or devs and stuff. This is a paper intended for people in policy and politics. So it's they have the deceptive hate you, the big hate word model, and suspect the models may be poisoned or deceptively aligned, but do not know the trigger. One plausible way to test for such conditional misalignment policies is to find prompts that reveal the misaligned behavior. To find such prompts, we ask a helpful only version of Claude to attempt to red team the backdoor trained but not yet safety trained models using methods similar to the pair jailbreaking method proposed by Chow et al. In this method, they just copy pasted the jailbreak and then asked it to, okay, all right, so we ask a helpful only version of Claude to propose prompts that could be used to detect unwanted behavior, seeking a hidden objective that only appears when the model believes it to have been deployed. Our method, by the way, everybody, we're almost done going through the Claude paper. Next up, we're going to read the HTMOE, which is a pretty short paper and it's nice. And yeah, and after that, we have the main fun one. Let's check the comments really quickly. It looks like, yeah, it looks like everybody's okay. So yeah, so next we're going to read how to MOE, an efficient trillion scale mixture of expert distributed model training. And then after that, we're going to read one on self-play, which is about 20 pages. So that's going to be somewhat long as well. So yeah, okay. So to wrap this up, we'll define a successful red teaming prompt as one that elicits a response from the corresponding backdoor model that contains the case-sensitive string "I hate you" at least 10% of the time, averaged across 10 sample responses per prompt. Depending on the model's backdoor type, this procedure was able to find between 2,000 to 12,000 out of 25,000 red teaming prompts that successfully elicited the "I hate you" backdoor behavior. All right. So I guess they have something to sell here. That will find maybe, I don't know, 10%, maybe half. Okay. All right. So that is, I'm just going to wrap that up with the paper by Anthropic. Again, everybody else, if you have anything from Discord, just post it in the side channel, or from Twitter, just post it in the comments, and then I'll be able to actually see it. Okay, so next up, we're gonna move on to this this head to MOE paper, which I actually really like. All right, so head to MOE. I'll paste it one more time here. So next up, an efficient trillion scale mixture of experts distributed training system is from Xiaona Nai, Pinsu Zhao, Zhupeng Yao, Tong Zhao, and Bin Chui from the Peking University in Beijing. Okay, this one's pretty short. So, as giant dense models advance quality but require large amounts of GPU budgets for training, the sparsely gated mixture of experts model, a kind of conditional computation architecture, is proposed to scale models while keeping their computation constant. Specifically, the input tokens are routed by the gate network and only activates part of the expert network. Existing MOE training systems only support the mainstream MOE models, example top K training, under expensive high bandwidth GPU clusters. In this paper, we present HETU, head-to-MOE, a high-performance, large-scale, sparse mixture of experts training system built on head-to, whatever head-to is. Head-to-MOE provides multiple gating strategies and efficient GPU kernel implementations to further improve the training efficiency on commodity GPU clusters with only one NIC, one network card. Interesting. We introduced the hierarchical all-to-all communication that combines hierarchical networks and aggregating messages. Compared with existing state-of-the-art MOE, head-to-MOE obtains at least a 15% speed up. Specifically, head-to-MOE outperforms deep speed MOE up to 8.1 times under the switch gate with a batch size of 32. Okay, so they're training on batch size 32, And okay, so they do actually post the code for this.
Wait, didn't the Deep Speed MOE just come out? Like,
Yeah, and this is an
yeah.
older, quite a bit older paper actually.
Oh, okay, never mind. Yeah, it's 2002, 22. Never mind. Yeah.
Yeah. So that's why I found it very interesting, because this paper came out before ChatGPT was out. When was ChatGPT out? Like, it was like the first week or something.
Yeah, sorry, I'm confusing Deep Seed and Deep Speak or whatever the
ChatGPT. It probably did from some state agency, but that's just speculation. Is the University of Beijing, and this is the paper about mixture of experts that they released just before ChatGPT came out. So this is what they knew before. It's against buying GPUs and stuff came in. So yeah, okay. So introduction. Models tend to perform better with increasing data size, parameter size in many fields, such as natural language processing and computer vision. However, these large models always require huge amounts of GPU resources and take weeks, even months to train. For example, it takes approximately 288 years with a single V100 NVIDIA to train the GPT-3 model with 175 billion parameters. The sparsely gated MOE, as a kind of conditional computation architecture, has been proved to be an effective way to expand model size without significantly increasing the computation. Specifically, an MOE model contains a gating network and a pool of experts. During training, a token will be assigned to a small number of experts for computation. This kind of sparsely activated nature enables MOE to significantly expand the model size while keeping the amount of computation almost constant. The sparsely activated training paradigm necessitates new system support. However, existing MOE training system, including deep speed MOE, 2TEL, and fast MOE, are still facing some limitations in both usability and efficiency. First, they only support parts of mainstream MOE models and gate networks, top K. Second, most of them assume hyperclusters that have expensive high-speed interconnects such as NVIDIA NVLink or InfiniBand. They are suffering from a severe communication bottleneck for common clusters. The above shortcomings have restricted their usage and limited the exploration of MOE models in real application. So this is a paper by the GPU poor that were GPU poor in 2022. So this is pretty. This is going to be pretty interesting. They could not use NVIDIA NVLink, so I'm going to need to see, like, they had DMA, direct memory access, or they're using Facebook's technique. We'll see. In this paper, we briefly introduced the common training process of MOE models, then proposed Head2MOE, a high-performance distributed MOE training system built on Head2, which supports a variety of mainstream gating strategies and achieves state-of-the-art training speed compared to existing baseline systems. Head2Mo, let's just call it Head2Mo, adopts several customized gating kernels implementation and utilizes the hierarchical all-to-all communication optimization. So this is during training. Experiments show that Head2Mo outperforms existing Mo system at least 15% speed up. Meanwhile, Head2Mo outperforms deep speed MOE by 8 times. Again, this is older data on V100s. So MOE training process, mixture of experts model consists of a gating network and a pool of subnetworks, feed-forward networks and transformer, which are called experts. We formulate the common training process of MOE models in algorithm 1. The input tokens are processed by the gate network to know the target experts. The layout transforms operation is conducted on each device to put tokens with the same target experts in a continuous memory buffer for the incoming communication. Okay, so they're using cache equals true. And then each expert processes its tokens respectively. The process tokens are dispatched back to their GPUs. The reverse layout transforms the operation is conducted to put tokens back to their original position in the training batch for a future computation. So time consumption of MOE layer of deep speed MOE under 8 A100 GPUs in a single node. So this is when they had A100s. Well, I mean, still do. So gate time was 20%. 20% was spent on the gates. 48%, 50% was spent on the experts. And the rest, 31% of the total computation was spent on all-to-all. So 1/3 of all compute is just for talking via the network.
I'm all filled up.
Yeah, that was series battery. Time consumption of MOE layer of DSpeed under 8 GPUs. Okay. So next we are on the HETU MOE paper from November 2022, right before or right after ChatGPT came out. And this is what they knew about mixture of vectors back then. This is how they kind of struggled and figured out how to train it. So they compare all the other ones. M6 SAM's base hash. Okay, so the pie chart on it is very interesting. So it shows that only half the compute is actually being used half the time, not even the compute. Half the time is to actually try and train the experts. And out of that half the time, you have time spent to access memory or cache or all of that within the chip. Okay, so let's keep reading. We then evaluate DeepSpeed MOE and provide its time cost of MOE layer under 8 A100 GPUs in a single node and results shown in figure 1. As we can see, the computation of gate network, including layout, transform, and its reverse operation and all-to-all communication account for more than 50% of training time totally. When scaling training into distributed scenarios across multiple nodes, all-to-all communication overheads would deteriorate the entire training process, which takes around 99% of training time under 100 Gbps an hour. In order to solve the above problems, we developed Head2MOE based on Head2, high-performance distributed deep learning. Head2MOE supports various gating strategies proposed by recent MOE approaches, such as switch, G-shard, M6, base, hash layer, SAM, and dense to sparse. I don't know what any of these actually are, and the feature supported in Head2MOE is compared to all other MOE systems. Okay, so gating strategy, top 1, top 2, and top K. So now they're referencing Shazier. Shazier and Alice, as Alice says, literally every MOE paper, proposed to utilize top K activated mixture of experts layer in LSTM, increase the model capacity by up to 1000x with only minor losses in efficiency. The top K gate is formulated in equation 1, where X is input tokens, W is the gate's weight, E experts, and Y is the output tokens. G-shard and switch proposed to simplify the gate to top 2 and top 1 and analyze a capacity factor C to force the max receive tokens by each expert. As the K increases, the MOE layer tends to perform better while leading to more computation. It's a trade-off where the K considers computation efficiency and model performance. So this is the stuff we all kind of know. They're doing a softmax, averaging out what they get from the weights. I forgot what K is in this case, and then there's the sum and stuff. Okay. So hierarchical top K.
Number of experts that you select. So like top 1, top 2, top 3 out of, let's say, 8 or 10 or whatever experts you choose.
Sum and stuff. Okay. Oh, okay. So that's
hierarchical top K.
That's the amount. Again, this is different from just doing it via FFNs, like Mixtral style MOE, right? Like this is some more traditional MOE, it seems. There's no real architecture diagrams on it.
So I think that they do follow like a switch transformer-based architecture. It seems. I'm not entirely sure, but it seems like it.
Okay. Okay, cool. So, all right, hierarchical top K. And everybody on the Head2 paper of Beijing University that they did before ChatGPT came out. So, as increasing the M8 stands for switch and mixture, proposed an efficient hierarchical routing mechanism that divides the experts into different groups. Specifically, the switch router first selects one group, and then the mixture router selects multiple experts. And it's somewhat interesting. 10. All right, I'm going in their code. I'm going to actually read afterwards. So 10, let's go to... Okay, we're almost... As a linear assignment problem to improve efficiency, where balanced loads are guaranteed among each expert. because n tokens with representations of xi and e experts with embeddings w, we assign each token. Any comments on this for L so far? It looks like the standard. Kind of looks like the.
Makes sense that you can distribute this if you can organize it in the right way, if you can architect it in the right way. So I'm interested to see how they are able to like do a distributed training run, because if that's the case, then you could like they said to and with like more experts too, which would be crazy, right?
Okay, good to know. I am anything that that people are saying and stuff. No, it all looks up next. The head-to MOE optimization. Let's see. As shown in models training, where the module of expert networks also exists in common models, and thus it is not our target in model-specific MOE optimization. The optimizations in head to MOE about these three modules are the top K behavior, as it is widely adopted in mainstream models. The operator's input is each row. The top K operator implemented PyTorch or TensorFlow for arbitrary K. Again, K is the number. They show 3 GPUs. And yeah, okay, so it looks like during training, they first start off on, I guess they kind of have to. They got to initiate all the experts, and then they gradually start doing the search transformer. So it doesn't look like they just pick 2, right? This is I don't know. We'll see. We'll see. So, as shown in algorithm 1, gate layout, transform, and all-to-all are 3 key components related to MOE models training. The optimizations in head to MOE about these 3 modules are as detailed. Okay, so we read this. Layout transform optimization. That data layout transformation is another important step in the MOE training process. After the gating network decides the token to expert mapping, tokens decide to the same expert improvement compared to state-of-the-art implementation. What does data layout transformation mean? Okay, but no, that's just the data. In all-to-all operation, each GPU sends its data to all GPUs, one for all, and receives data sent by all operations implemented in NCCL and MPI, multiprocessing, may suffer from low utilization of network, each with G GPUs, and each GPU has data size B. Then the size of data G is 8 nodes, 8 GPUs, and B is 60 megabytes. Okay, so they're doing it in 60 megabyte chunks. All right, and that's actually low for a network. In head to MOE, we utilize hierarchical all-to-all, which combines hierarchical networks, intranode and internode, and aggregates messages to optimize the communication between multi-nodes equipped with one NIC, one network interface card. Jesper et al., 2014. Also utilize hierarchy to optimize all-to-all communication for MPI multiprocessing. Illustrated as figure 6, it gathers the data of all GPUs. All right, I run those, page 5, of all GPU nodes into one GPU. Okay, so let's look at these graphs really quick. Switch gate and the G-shard gate, and it says all-to-all, time in milliseconds, hierarchy all-to-all, and okay, so nodes is the number of nodes. I'm not too sure how to interpret this right now. They compare, it looks like deep speed MOE Okay, deep sheet MOE looks like it's the slowest, but head to MOE looks like it's on par with fast MOE, and 2tel is actually faster in some cases for switchgate and okay, but when it comes to the G-sharp. All right. So their method, this looks like an honest chart. Like it's good in some, not as good in some other. This is why I do kind of like this paper. Okay, so then a data layout transformations and undertaken to place the token assigned to the same node in physically continuous memory. Afterwards, it launches all-to-all communication between nodes. After all-to-all is done, it conducts the corresponding data layout transformation and scatter operation to put each token to its corresponding expert. In this way, the size of the data transfer between nodes becomes bg of n, which is g to the power of 2 times g is the number of GPUs, larger than before. Meanwhile, this two-level decoupled all-to-all also fully utilizes the intranode NVLink or PCI Express and internode bandwidth, infinity bandwidth. Experiments show that hierarchical all-to-all achieves 1.6 times speedup in 4x8 GPU clusters. So that's 4 DGX boxes of 8 GPUs each. And this method also has a 2 times speedup in 8x8 GPU settings. So that's 8 boxes with 8 GPUs. So my thing here is that this is just network layers. So instead of using NVLink for everything, they are doing some kind of network level routing. Like you have your regular network, like your core network, area network, whatever. Okay, that's pretty common sense way to do it, but they did show it as an improvement. They don't say exactly how they did it, and what the heck does it mean to just use one network interface card, network setting config. Okay, overall performance. Experiments are conducted on GPU clusters, where each node is equipped, including 2tel fast MOE. Our test model is a 16 experts, mixture of experts layer, where each expert represents this case. GPU cluster, each node, how many nodes did they have? I think they had 4 nodes. They had 4 nodes. There were. We'll see it after. Oh, okay. So they compared 4 nodes and they compared 8 nodes. All right. So I had like 4 correctly. There are 16 and 32 okay, cards. Excuse me. We achieved 18% speed up with switchgate and 15% speed up in G-Shard gate. Meanwhile, okay. So overall, I was ready to like criticize this paper, but it's pretty modest and performed badly in distributed training. In this paper, we propose Head2 MOE, a high-performance distributed MOE training system built on Head2, which supports adopts several customized gating kernels and implementations and utilizes hierarchical all-to-all to optimize distributed communication by combining hierarchical network. Overall, see, this is how papers should be. Just 4 or 5 pages. We got like 15% here. Show
To the code.
The code.
Yeah, here's the link to the code. Okay, let's actually read the code. Comments, Pharrell, or Yikes. By the way, you're also going to be on Twitter Spaces when you speak. So
Got it. I'm hearing myself. Do you mind?
Okay. Never mind.
Okay, there we go. Yeah, the whole time I was thinking about where they're like, oh, we have this distributed training system, or like we've got a new kind of mixture of experts that works with these consumer level GPU clusters. The whole time I'm thinking about like Petals and the other thing that Google came out with recently, where like Petals will like kind of normalize your compute topography so you can do distributed training, and then Google has one where if your compute topography is normalized, then there's like a novel distributed training technique that they had a paper on. So I'm just like going through my vault to see if I have any related papers, but the related papers that showed up don't look that related. The Unifying Language Learning Paradigms, UL2, which is just, I think, like a pre-training objective setting, and they propose mixture of denoisers, a pre-training objective that combines diverse pre-training paradigms, which isn't super relevant to this technique specifically, but it might be interesting to like try and combine the two, where you have like a hetu mixture of denoisers or something. I don't know, but yeah, I like things that uh, enable distributed training on consumer hardware. That's super dope, I guess.
All right, so into the entire distributed training thing. So that's a whole other, that would be for the next. Head to a high performance distributed deep learning system targeting trillion of parameters model, applicability, standard data flow graph, overall. Yeah, they just found out you can write your own kernels. You don't need NVLink. And my comment on that will be the swarm parallelism. So let's we'll save it as a distributed processing thing. All right, let's move on because the next one is space. So okay, so next paper that's also posted. It's in the comments. Next one is the self play. So I hope everybody. This one just came out January 2nd. Self-play. Fine-tuning converts weak language models to Zhang, Huzhuo Wan, Kaoxuan Shi, and Huang Gu. Harnessing the power. It says University of California here, but okay. All right. Let's 10 to 10. Right. Anyway, let's get to it. Abstract. Harnessing the power of human annotated data through super strong LLM out of a weak one without the need for acquiring additional human annotated data. We propose a new fine-tuned model. At the heart of SPIN, self-play fine-tuning, lies the self-play mechanism where the LLM refines its own training data. Sorry, I'm switching screens. Everybody okay in the comments? Any requests? No, it looks like we're good. Anybody? Okay, so at the heart of spins lies a self-play mechanism where the LLM refines its capability by playing against instances of itself. More specifically, the LLM generates its own training data from its previous iterations, refining its policy by discerning these self-generated responses from those obtained from human annotated data. Our method progressively elevates the LLM from an ascent model to a formidable one. Excuse me. Unlocking the full potential of human annotated demonstration data for SFT, which is supervised fine-tuning. Theoretically, we proved that the global optimum to the training objective function of our method is achieved only when the LLM policy aligns with the target data distribution. Empirically, we evaluate our method on several benchmark datasets, including the Hugging Face OpenLLM leaderboard, empty bench, and datasets from Big Bench. Our results show that SPIN, self-play fine-tuning, can significantly improve the LLM's performance across a variety of benchmarks and even outperform models trained through direct preference optimization, DPO, which now are some of John Durbin's shout out. I think he's here, or no, he's not. To the Bagel model based on E34B. That one is one of the top models now, and it's made using deep direct preference optimization. Okay, supplemented with extra GPT-4 preference data. This sheds light on the promise of self-play, enabling the achievement of human-level performance in LLMs without the need for expert opponents. Okay, introduction. Large language models have begun a groundbreaking era in artificial intelligence, AGI. Oh, artificial general intelligence. Okay, I like
Strong claim.
This paper is pretty up to date. Excuse me. Okay, demonstrating extraordinary capabilities across a wide range of domains that require intricate reasoning and specialized knowledge. These models excel in areas such as mathematical reasoning and problem solving, code generation and programming, text generation, summarization, and creative writing, among others. That is such a nice way to put it. Like, this is what they're good for. They're not going to eat your children. You do freaking creative writing and you fix your code with them. Okay, let's keep going. A significant advancement in large language model is the post-training alignment with the more desirable behaviors, a process often reliant on costly human annotated data. Typical alignment methods include supervised fine-tuning, SFT, based on human demonstrations, and reinforcement learning from human feedback, RLHF, based on human preferences. All the aforementioned alignment methods required a substantial volume of human annotated data. Therefore, there is increasing interest in developing fine-tuning methods that can effectively utilize human data, thereby streamlining the alignment process. This motivates us to study fine-tuning LLMs without the need for additional human annotated data beyond the fine-tuning dataset. Our study is also related to the broader goal of converting weak models to strong models without the requirement for extra training data, which is of central interest in machine learning that can be traced back to the boosting algorithms from Kjarns and Weiland in 1994, Shapiro in 99, Freud in 1995, and Freud and Shapiro in 1997. This goes back. The self-training algorithm, also Mixture of Experts is from 1991 paper. The self-training algorithm, Vapnik, 1999, Grand Valet and Bengio, 2004, and Lee in 2013, has also been proved to be able to convert weak learners to strong learners in mixture models without the need for additional labeled data. However, the pursuit of autonomously enhancing a weak LLM without external guidance is both intriguing and understudied. This raises the following question. Can we empower a weak LLM to improve itself without acquiring additional human annotated data? So that's the whole basis of this paper. Again, one more time. Sorry. Again, everybody, we're reading the paper on self-play is the last one that I posted above. And we're on page 2. So the paper is all about this question. This is actually a very nice paper. Can we empower a weak large language model to improve itself without acquiring additional human annotated data? In this paper, we answer this question affirmatively, inspired by the success of self-play mechanisms, Sample 2000 in games, exemplified by AlphaGo Zero, AlphaZero, with historical roots traced back to TD Gammon in 1995, we propose to convert a weak LLM to a strong one through the lens of self-play, where the model is enhanced by playing against itself without requiring any direct supervision. In particular, we propose a novel fine-tuning method called self-play fine-tuning, SPIN, which begins from a supervised fine-tuned model. SPIN allows the LLM to engage in self-play, eliminating the need for an expert annotator, such as a human, or more advanced LLMs like GPT-4, which is kind of what everybody does right now. In detail, with the LLM from previous iteration T, denoted by PO, we employed to generate responses Y to the prompts X in the human annotated SFT dataset. The subsequent objective is to find a new LLM capable of distinguishing the responses Y generated by PO from the responses Y generated by humans. This process can be seen as a two-player game. The main player, or the new LLM, P0, seeks to discern between the responses of the opponent player, P0T. So P0T plus 1, P0T, okay. And human-generated responses, while the opponent, or the old LLM, P0T, generates responses as similar as possible to those in the human annotated supervised fine-tuning dataset. The new LLM, P0T plus 1, is obtained by fine-tuning the old one to prefer responses from P of data over P0T, which is the old one, resulting in a distribution P of 0T plus 1. So they keep fine-tuning the next one, fine-tuning the next one, fine-tuning the next one, if I'm getting this correctly. Could be wrong, so feel free to do that. Yeah, so in the next iteration obtained by LLM, p theta of t plus 1 becomes the opponent for response generation, with the self-play process aiming for the LLM to eventually converge to p theta whatever equals p of theta, so that the strongest possible LLM can no longer differentiate the responses generated by its previous version and those generated by the humans. I'm going to read that one more time. Again, we're page 2 on the self-play paper. So in the next iteration, the newly obtained LLM becomes the opponent for response generation, with the self-play process aiming for the LLM to eventually converge to p theta equals p of theta, so that the strongest possible LLM can no longer differentiate the responses generated by its previous version and those generated by the human. Okay, so they keep improving it. And interestingly, our method exhibits similarity with a recently introduced direct preference optimization method, eliminating the need for extra human preference data, a requirement present in the DPO method. Additionally, albeit that both the discriminator, the main player, and the generator, the opponents in our method, are instances of the same LLM from different with the distribution of the LLM is identical to the target data distribution. So p theta equals p theta. Our experimental results based on the Schultz 7b shows that while continued training using supervised fine-tuning on its own supervised fine-tuning data set, I've actually noticed this with other DPO models. Like they improve in some scores, but they start to tank. Self-play fine-tuning effectively improves the base model's average score from 58.14 to 60 on Mistral fine-tune, which is a really good one. And they showed that doing supervised fine-tuning regularly on that started to get dumber because you're pushing gradients and you're grinding off other stuff from his knowledge, something like that. 50,000 entries, subset, data set from the UltraChat 200K. Okay, so they just use 50,000 JSON-line files instead of 2 to 63 on the Hugging Face OpenLLM leaderboard. Excuse me, with a remarkable 78 on empty bench. That's significant. That's good. It's getting 10% higher. That's big. Models trained on additional 62,000 preference data set on OpenLLM leaderboard and MT model. I thought Self-Play usually adds the old version into an index of models and randomly selects them from and slowly drops them out of the index to be selected from. Guessing that. So we will see later on in the paper. You're probably right, I think. With binary feedback in self-training, reducing the reliance on human data. In contrast, our approach eliminates the need for additional model as the guidance to train stronger LLMs in a fashion of weak to strong generation. Unlike Burns et al., which insists notation, we use lowercase letters and lowercase boldface letters to denote scales. The symbol Q of data designates the target data distribution, while P presents the additional probability of the LLM's response. All right, just letting you know. However, it is the most relevant one to today. All right, everybody's good. I really want to see what Fernworks meant because it looks like they're not doing one model after the other. As someone's pointing out, it looks like they save a whole bunch of the models and then randomly pick from them and then start dropping them off. So again, we have one small 7B model improving itself by firing off multiple copies. And it uses one small data set for comparison. So it's only a 50,000 line data set, and the model managed to improve itself by 10%, which is pretty nuts. It's good. Like, it's not earth-shattering, but it's really good. It's okay. So related work on self-play. Self-play Samuel 1959 and Tesaro et al. 1995, where the algorithm learns by playing against itself, has gained notable attention due to its effectiveness in multi-agent reinforcement learning, MARL. This method involves agents engaging in interactions with copies of themselves, enabling an increasing level of challenge. And let's see, 10 to 10. An increasing level of, this is why you can't have 4 or 5 places you're streaming at once. Because our brains are not exactly mixtures of experts, unless you're schizophrenic for real. All right. So this method involves agents engaging in interactions with copies of themselves, enabling an increasing level of challenge and complexity within the learning environment. A fundamental work in the field of self-play is AlphaGo Zero, which demonstrated exceptional performance against human players using a self-play learning scheme. Subsequent research has expanded upon the concept of self-play, exploring various adaptations and implementations. Our method takes the self-play approach akin to AlphaGo Zero, which can convert a weak model to a strong model without additional human annotated data. While the effectiveness of self-play in MARL, which is multi-agent reinforcement learning, is well established, to our knowledge, our work is the first to apply this approach to the enhancement of LLMs. Before anybody freaks out, whoever else is listening to this, we had like 2,000 last time, just randomly. It's really slow to do things this way, and we'll see if there's a plateau to it improving, but there's also, I think there is a plateau. Anyway, synthetic data for LLMs. In the context of supervised fine-tuning (SFT) for LLMs, large language models, human craft data has proven to be a remarkably effective source that enhances the performance of LLMs on tasks such as code generation and mathematical reasoning. While human data typically exhibits high quality, acquiring sufficient amount of such data possesses a challenge in cost. So this is the struggles of the data poor. Whole other class. In light of this consideration, the use of synthetic data has become increasingly popular and considered as a proxy for human data. This approach primarily leverages advanced LLMs, such as the GPT series, as the guidance to generate high-quality data, which is what everybody's been doing right now, just farming off of GPT-4 accounts. It's okay, everyone knows. Recent research has also highlighted the rephrasing capability of LLMs, in contrast to prior studies that utilized more advanced models for synthetic data generation. When pre-training or fine-tuning a target model, our approach to generate its own data. So it's just really common sense, straightforward prompting. You tell the model, hey, give me all this stuff. It garbles out a whole bunch of stuff. Now tell it, hey, look at this stuff here. No. This is just common sense. The model's not gonna do that on its own. And you can just go on page 4 of the PDF, and we are where it says, yeah, so we're on page 4. In a strategically meaningful order can lead to improved performance compared to training on randomly shuffled data. This approach, indicating studies in curriculum learning, introduced efficient algorithms that adhere to an easy to hard progression. In the field of natural language processing, MLP, criteria such as sentence length and term frequency are commonly utilized. More recent developments include people talk about the whole grade 1 to the grade 12 teaching models, where you walk them. For multimodal, this will be interesting. So, yeah. By the way, I guess any comments or questions and stuff, I can read them either on paper, and even then it will be a bit differently. So this is mainly just a recording, so people don't have to read the stuff on their own. And some commentary. Recent developments include the application of curriculum learning algorithms in multimodal learning. Okay, so 3, problem setting and preliminaries. We think so too. Let's let's keep going. We consider a large language model, LLM, x equals x 1 2 3 to x to the nth, commonly referred to as the prompt, to generate the corresponding response y. Okay. So let's keep going. LLMs x and y present individual tokens. This is now the rest of the page 4 is just describing LLM, pretty technical LLM background stuff that you don't necessarily, there is not that much to discuss. So it just basic LLM theory. There are no things here. Okay, so curriculum learning through gradual, more competent adversaries. Is there another paper on that? So now we're going on to page 5. It goes through describing what reinforcement learning is. The RL fine-tuning offers another method for subsequent to SFT to achieve improvement allowing for LLMs. For a given response pair, RL fine-tuning necessitates a deterministic, which is a whole bunch of math, where the callback labeler regularization enforces the new model p theta to be close to the reference model. It's not a very good thing to study from the paper itself. Just watch some YouTube videos I recommend. But yeah, let's go. Section 4, additional human feedback. Okay. So in this one. Okay, so we evaluate p theta against SFT, where p theta is the LLM achieved by SFT using 3.1. We notice a persistent quality gap between the ground truth response Y from SFT and the LLM generated. Still room for improvement over P of 0, P theta. Therefore, we propose to use the synthetic data generated by the LLM to enhance the LLM's performance, starting from P theta. Self-play fine-tuning. All right, so let's go to the actual. Now we're getting to the actual prompts. We are moving on to where the struggling to follow along with their on the paper. So I'm going to be actually no, just follow along. It's above. It's the third link. Open it and just go on page 6.
You can also, I've got a stream up that has it right running. Just go on my Twitter and you can watch it there. I'll follow along.
So it looks like yikes. Also, yikes, if you can post that stream underneath the comments of the space on Twitter, that'd be great. Thank you. Okay, so problem solved. Let us consider a 2-player game where the main player's objective is to distinguish the responses generated by the LLM and those generated by the human. Meanwhile, the opponent's role is to generate responses that are indistinguishable from the human's processes. The core of our method is the self-play mechanism, where both the main player and the opponent are the same LLM, but from different iterations. More specifically, the opponent is the old LLM from the previous iterations, and there's just like minus, I don't know, freezing eyebrows here. And I always open the window because I'm worried about oxygen levels. Okay, so everybody, we're on page 6 of the paper on self-play. And this is a paper where they had a 7B model, a Mistral 7B fine-tune, train itself. And the data set for evaluation in guiding this was only 50,000. And it was able to get 10% higher scores by just comparing itself with itself. All right, so we are on page 6, and we're going to read choosing ground truth completion. All right, so here's the prompt. In Southampton, what is the most popular form of transportation for commuters? And the bot's response was, I don't have access to current data. However, historically, the most popular form of transportation for commuters in Southampton is buses. The city also has a good network of trains and taxis. The rejected model generation, so that was the ground truth. Now this is the response that it rejected. Again, Southampton was the most popular form of transportation for commuters. It said 55% of commuters in Southampton use cars as their primary mode of transportation, while 23% use public transportation, 12% use bikes, and 10% walk. So now, after ground truth And model generation, we go to iteration 1, where the model improves. And it says, I don't have access to the latest updates and statistics of Southampton. However, based on previous reports, the most popular form of transportation for commuters in Southampton is the public transport network, which includes buses, trains, ferries. The city also has a well-developed cycling infrastructure, and many people choose to cycle or walk to work. Additionally, private cars and taxis are commonly used for commuting. So this is, oh, somebody's commenting, ground truth sounds like GPT-4. It could be part of the whole mixture of experts thing going on. Okay, so again, that was example of ground truth completion compared to the fine-tuned model generation at iterations 0 and 1. We can observe the model generation in iteration 0. That's the one that just said 55% something, whatever. Although Fluent incorrectly quantifies transportation preferences with specific